So we know the two categories of electrical motors, right? Then we talked about DC motors, shunt motors, separately excited motors, permanent magnet motors. These are all that we have on our manufacturing line of permanent magnet motors. Looked at series motors. Sometimes these can actually be used on AC or DC. Talked about compound motors. Talked about how we reverse them. Looked at a little pulse width modulation, and I didn't bring my camera over. But I have one set up. I'll try to go get my camera. Looked at reversing. Standard way we reverse the DC motor is to reverse the armature or rotor. We looked at different reversing circuits. This one used in transistors, but they work the same way, guys, no matter whether they're solid state or whether they use relays. Is we turn these things on in sets. And so we don't actually change the polarity to the circuit. We change the way we switch these on. So this H control here, if this one's on, this one's on. Then of course current would be flowing up through the negative, which would be here, and it would go through the motor in this direction right there, and then up through here. And then we'll look at the diagram because this is not what our over here it would be the same thing. This one is on, and this yeah, I needed that. This is one I can't see. Oh, they have it on. Didn't plug it in. So I didn't turn it off. Okay, sir. So this one, if this is an FET, by the way, this right here would be on, and the current flow would be up through here in this direction right here, and then going up to the positive, right? And then I'm just going to change colors so we can see it. Then we return. This will turn off. This guy here would turn off. Then we turn this one on and this one on. And then current flow would be up in the opposite direction, so the motor would change direction. And then the same thing would be true over here. So you can see why this is called an H control. Ours don't use solid state. Ours actually uses relays. So this is the control that we have. So we have two relays that are actually controlled by an output of the PLC. I don't know. We'd have to look it up. And then this is going to pick up a motor. This is going to pick up a motor. We'll call this one forward, and then we have an output. One of them is forward, one of them is reverse, and then that would come over here. And this would be RED. Now, normally what they should do if they were a good programmer is if I make a mistake in my program and I energize both the forward and reverse at the same time, then that would close this contact, that would close that contact, and we got a direct short. So normally what we do, just to prevent from this happening, is we'll put a electrical interlock, and this one would be controlled by the reverse, and then this one would be controlled by the forward. And then that way, if these two contacts close at the same time, one of these relays are going to be faster. But there's no way in the world I can do two of them at the same time. So then what we do is we come over here, and the actual circuit would be, our relays would be like this. These would be the contacts of the relay. And then our armature would be right here. And if this is forward, well, let's say this is the contact being closed. let's say I leave this alone, and I don't have them in there. And I'm a programmer. I go here programming my thing, and I screw up on my program, and I accidentally in my program cause this contact to close and that contact to close. What's going to happen? That's going to close this guy right here, and that's going to close this guy right here. And now we have a direct circuit between minus and plus, so we have a short circuit. Okay. But if I come over here and put a forward right here, I mean, if I come over and put a reverse right there, and then down here I put a reverse, then there's no way in the world these two can energize at the same time. So I come over here and I energize my reverse. Let's say this contact closes. Reverse comes in. Well, then I accidentally close that one. Well, if the reverse comes in, then this contact right here is going to open. Understand? Yeah. So that means now I can't get through to the forward. So there's no way in the world these two contacts can close at the same time with that electrical analog. Now, one of ours has it. I'm sorry. And then, of course, what we also do over there is that they also have what we call a mechanical interlock. And I think I showed y'all that, where if I manually push down on the forward, it wouldn't let me push down on the reverse, on the override, on the manual override. So that's the best way to do it with both electrical and mechanical. So that way I can't accidentally make a mistake inside my PLC program, and then some idiot over there goes over there and tries to push both of them at the same time. Because if you do, you're going to have a short circuit. So this is actually we can show y'all the schematics. So I'm going to come up here and I'm going to bring up the schematic for module. Let's see. I want to get back to the Amatro line module 2, and then we'll come up here and look at the. I think it's this one. It's one of these input-output charts that gives us the actual wiring of everything. No, just to show it. These are the two relays right here. Motor starters, but they don't give us somewhere. Let me bring up the entire book. Let's see, PDF combined. Okay, so here it is. So this is the actual wiring of this. So here's the DC motor. And
Mr. Raymond, you're not sharing your screen with us.
well, thank you for that too. So y'all wasn't seeing the PowerPoints or anything. So, and then what we did is we switched over to the actual wiring of the motor. So, this is still not it. Okay. Oh yeah, these are the start-stop buttons on front. These are the two relays. I don't know which is which, but if I come over here, so here's 0, or this is minus, and this is plus, and I can't draw this. Let me pause this and do one more actual wiring of the motor. So my interlocks are inside the PLC program. So what we have on the PLC program, some of y'all's had PLCs, then we would have whatever they call it, I don't know, but FD. If a programmer is good, if they don't do this, then we might have a problem. If I was to get in there and start playing around with this program, well, what I should have in the PLC program is the one that I showed y'all, where this right here would be reverse and this right here would be forward. But you can actually see, so let's say we energize K4. Well, if I energize K4, this contact's going to close and this contact's going to close. So we'll drive from minus, so it'll come through, it'll go through the motor in this direction, then it'll come back and go to positive. Okay. So if I come up here and I'm not, if I come over here and energize K5, okay, talk about okay, drawing thing. So, here it is. So if I come over and energize K5, so in that example, the current flow was in this direction. Well, if I energize K5, and let's see this in a different color. So K5 is energized, so this contact will close, and this contact will close. So now my minus comes in, okay, comes over here, drops down, comes over here, goes through it in this direction, comes back, and goes back up. So this is the way it's drawn here, but it's easier to see if we come over here and draw it as an H control, which is what this is, it's just drawn a little different. So this is minus, and then this right here is plus, and then of course my motor would be, my armature for my motor would be right here. And this right here, if this right here is K4, then this over here is going to be K4. If this over here is K5, and then this down here would be K5. Now this is the reverser that we have. The electrical interlocks are not in the relay coil, so the electrical interlock should be inside the, but it does have this. So it's got a mechanical interlock, so I can't force them in at the same time. You know, I showed y'all last class how we can actually move this carriage back and forth by hitting the relays. But I could not do what? I couldn't push them both in at the same time. If I ever let these two relays come in at the same time, then that would be a problem. And this is what we're saying. So a good programmer would actually put these software interlocks. So if I made a mistake in my program, I could not, so if I close K5 and K4 at the same time, these two contacts close, then we got a short circuit in our system. Wouldn't hurt your motor at all, but it'd blow a fuse or something like that. So this is the control that we use, but if you look, they're all basically the same, except for this guy. Now, the problem with this guy is this is plus, and this is minus. So right now, current flow would come minus, would come up and go through the motor in this direction, and it would come back and go this way. If we come over here and switch it in the opposite direction, so that way it was, so let me do red again. Red is this direction right here. And then if I switch it in the opposite direction, now let me use another color. So I'll switch this over here, and now current flow is going to come up, going to go through the motor in this direction, and then come back and go back But, now, what's the problem with this? So this is kind of the control. It's a little different, but this is the kind of control. If you got that ceiling fan, this is the kind of control you have. So you got a switch that you go between forward and reverse. You got that thing running third speed forward, and you click it down to reverse. You hear that motor humming at you because it's trying to reverse, right? You understand? And it pulls a lot of current. We call that plugging a motor. Plugging a motor means you try to reverse it, change its direction before it comes to a complete stop. This control right here, this guy right here, plugging, reversing a motor without stopping. Pros, very simple circuit, can be done with a double pole, double throw relay. Cons, draw starting current until the motor changes direction, which reduces the lifespan of the motor. Stopping the motor requires removing the power. So over here, on this one, on the H control, all I got to do between reverse and forward is just de-energize both relays. If I de-energize both relays, then of course now the motor can do what? Can come to a stop, which is what you should do. So what you should do when you reverse your ceiling fan is turn the thing off, right? All right, go flip it 3 times, wait till it does what? Comes to a stop, and then reverse it. You'll get a lot longer lifespan on your motor. I had one actually burn up on our bed, and it dropped sparks down on the bed. Lucky nothing caught on fire. That was an experience. So this is the control the Amatro line actually has on. The Festo line has no motors that need to be reversed. But you can always see each time when it comes back, it stops, and then before you can do what? Before you can change direction. So we don't plug the motor. So plugging the motor is when you do what? When you reverse reverse its direction, because reversing forward to a motor is relative. It's relative to how the motor's hooked up. So in one situation, clockwise could make it go forward, but in another situation, clockwise might be reverse your application, right? So a motor turning, there is no reverse and there is no forward on the motor itself. It's either going to run counterclockwise or clockwise. So this is the actual circuit that's on the Amatro line. And like I said, they don't show the electrical interlocks. I would like to actually look at the program and see if they've got those interlocks in there. And then we looked at 7 motors, looked at brushless DC motors, and then we got into AC, got into single phase motors. We don't have any of these on our manufacturing line. All ours are DC motors. Talked about capacitive start motors, talked about capacitive run motors, talked about shaded pole motors. Then we got into 3-phase. So this is basically where we stopped at. So any questions so far? We can do it. We can do it that. What we would do, it depends on the stepping motor and how it's wired. We have different ways we can do it, but normally one way we do it is it's got 4 windings around it. And what we can do, it's just not always true, but we can come over here and like connect one end together. And this way the thing would only run in one direction. That's not true. And then I could come over here and use a BJT or an FET to actually come in and actually do the switching for it. But basically, what we do, and then each one of these would have its own transistor or whatever. Of course, I need to put that up there. And what we do to make it run in one direction is we might fire them counterclockwise, and the motor would do what? Run clockwise. If we fire clockwise, and the motor would run clockwise. I've got a stepping motor circuit hooked up, but I can't find my program that runs to Arduino. And what's nice about a stepping motor is it moves in steps. So our stepping motor has 100 steps, and you can actually feel them, guys. I'll see if I can find one. And in 360 degrees, that means we would get 3.6 degrees per step. This is accurate. And so you can actually see it on the module 3. That's the motor that it's running. You can hear it on a robot a lot because the motors will sing at you. So if the motors sing, that's probably stepping motor doing that. I'm not saying it is, but it's a high probability that you hear the motor singing. But those, what's nice about a stepping motor, most stepping motors, is we can run these without feedback. So we can run them open loop. But what we have to do is we have to start them from a reference point. So I think I showed y'all that. Did I show y'all that on the carousel? Well, I stopped it in the center and turned it back on, and the thing actually found itself. Did I show y'all that? I did the other class. I'll show this class today, and then I know I showed y'all that on the other group, right? Actually, the carousel how it zeroed itself. If I didn't, y'all need to remind me, and I'll show it to this group. I'll show this group today. So yeah, yeah, the carousel. Well, I started it running. I clicked it off, got it out in the center. I turned it on, and what it does is it starts stepping, moves real slow and stepping. And what it's got the top is made out of aluminum. I'm not doing a good job drawing this. But down at the bottom, under the bottom, they got a metal plate under there. And what the stepping motor does, it's going to step it in the clockwise direction and it's got holes until that inductive sensor clears that hole. And then it'll step it back so many steps. So I'll show y'all that today. Let me remind me that when we go back to the line, which we might be able to. Today is troubleshoot day, by the way. So every one of y'all's sections have got bug problems. So that's a good question about stepping motors. What steps them is usually bipolar. You can buy integrated circuits that run a stepping motor. These have been around so long. So integrated circuits, I've got a little circuit that actually uses a counter, which is pretty neat, but I'd have to show it to you. So we looked at three-phase, and then we talked about the DC motors. This is the way we calculate the speed of a DC motor. A speed control is not normally controlled with voltage. If voltage is lowered, both speed and torque decrease. If voltage is increased above the rated voltage, torque increase, but speed does not. Speed can be changed by changing the number of poles, which this is what you're doing on your ceiling fan. When you put that thing through three things, if you ever pulled it off, it's got a common coming in. It's got three outputs on it, and all you're doing is with each three output would select the number of poles. So this right here might select 2. This right here might be 4, and this right here might be 6. And each one of them would slow down. So the more poles you add, the slower the motor would run. So your ceiling fan is a 3-speed fan, and that's what you're doing. But changing the number of poles, you don't have an infinite number of variations between speeds. It's going to be precise, right? So this right here would be 3,600, and this right here would be 1,800, and then this right here would be 900. And that would be the only speeds available to you. So if it didn't have any slip. So the RPM is actually set by this, 120 times the frequency you're running it at, divided by the number of poles. And so that means if I've got a rotor, and then we've only had 2 poles on the stator, and that would be what we call a 2-pole motor, minus the slip. Now, AC motors have to have slip, because if it don't have slip, there won't be any motion between the rotating field and the stationary, between the two, two rotating fields. So to get motion, and y'all can't see me, let's see, I don't have I don't have my camera hooked up. So if we've got, we got a rotor, it runs off induction. These are induction motors. So what happens is if these guys get in sync with each other, then there's no difference to create the relative motion between the two. So that means the rotor will always have slip. So a 4-pole motor might be rated, if you looked at the RPM on the motor, it might be rated like 1725. So the field's running at what? The field is running at 1800, but the rotor only runs at 1725, which would be 65 difference, right? Between, and that way, so this is the speed of the field that's moving around the outside of the motor, and then this would be the speed of the actual rotor itself of an induction motor. If you're looking at the nameplate, I don't know if I have nameplates on the motor. See, I know I probably don't in this class, but it would be good for me to bring that up. I know I've got them in motor controls. So this is a typical motor nameplate. If it comes up. So this is the horsepower rating. So this is 725. So that would be, I know it's a 4-pole motor, right? And then that would be 65 slip. This is the frequency it's designed to operate. This is the 3-phase motor. So the service factor tells us how much we can legally overload the motor. So that means it's got 0.5. This motor cannot be overloaded. So what you do with the service factor is you take the horsepower of the motor and multiply it by the service factor. So this motor can't be overloaded. This would be dangerous to plug. This guy can run between 208 or 230 or 450, so we can rewire it. If we're running at 208, it's going to require 1.6 amps to produce the horsepower. If we run it at 440, it's going to take 900 milliamps to produce the horsepower. So if voltage goes up, we're dealing with power, right? You understand? So if voltage goes down, then the current's got to go up to produce that same horsepower or that same work. So normally on circuits, but you have to rewire the motor. So you have to rewire the motor for high voltage. If you take motor controls, or if you take AC/DC machines, then Mr. Sanders or me will show y'all how you can rewire a motor to run on high voltage. This is a continuous duty. It's what else I want to say? Amps. By the way, this slip is if the motor's running at its rated horsepower with its rated voltage. If you run it on a lower voltage, it's going to have to create more slip to get the horsepower. If you run it at a higher voltage, then it'll try to produce more torque. So we don't really want to do that. This is the full load current, we call it full load current. This is the current that the motor will run if you're running at its rated horsepower and at its rated voltage. So this would be this would either be a label that's on the motor or it's going to be a metal plate that's on the motor that shows you all this information. Continuous duty means this motor was designed to run 24 hours a day, 7 days a week. Enclosure, you'd have to look these up on the chart. This shows you the actual way the thing mounts, how it mounts. And this code right here would give us an indication of what the start current would be. So that's actually a nameplate. So what we're saying is all these induction motors have to have slip, so they'll never run at the full speed. Now the problem we have on a variable speed drive, which most people call a variable frequency drive, I think I showed y'all this last class. So normally we'll bring if we're going to control the speed of an AC motor, we got two options. We can control the poles, which has been the preferred way for years. Or it says we can control the what? It says we can control the frequency. Now the problem with controlling the frequency, if you had AC, is that the opposition the motor gives is set by that formula right there. So this determines how much current the motor pulls. So what happens is if we raise the frequency, then opposition is going to go up, which means I is going to go down and the motor stalls because now it can't produce the horsepower. If we lower the frequency, then current goes way up, and then we create a lot of torque, and we can tear stuff up, and we can still burn motors. So what we have to do when we program these variable speed drives is we take that chart I said, and this is all you do, is real easy, is you enter two things. You enter, well, that's not true, but the two things you enter is the voltage, and then you enter the frequency. And then then it calculates what they call a volt per hertz. So what that means is, 17, 25, 60, then we would come up here and we would, so we take 1725, we would divide it by 60. Oh, I'm sorry. We would take volts per hertz. We would take 60. So what was the voltage it was rated at? Let's say 208. And then we divide it by 60. And this would give us what we call our volts per hertz. What does that come up to? Anybody got a calculator? Okay, so 3.46. What that means is I could put 1 hertz on that motor, but I'd have to drop the voltage down to 3.46 volts, and the motor would produce the right torque and it would run at that speed. If I put 2 volts on it, then I would put 6 point. So that's all the variable speed drive does. It just raises the voltage and the frequency together. If it's running at 1725, then that means it would be putting 208 volts out. So, and that's the way you program it. Well, basically, the way you program a variable speed AC drive, you just enter this information right here, right off the nameplate, and then the rut. So they called it so it's got a bad name. They called it a variable frequency drive. But if you just change the frequency, you'll either burn the motor up or you'd stall it when you try to change the speed. So they're changing what? They're changing the voltage and the frequency together to cause the thing to run. So I like to call them variable speed drives, but everybody corrects me. So, you mean a variable frequency drive? And that's what they're called in the industry. And I showed y'all this, and we showed y'all this. So they use what we call pulse width modulation on these variable speed drives to change the frequency and also change the voltage. So if I was to come over here and bring these closer together, then that would change the frequency. If I make the pulses wider, that would change the voltage. So this is basically showing you how the voltage changes. So this is the way a variable speed drive works like this. It's pretty cool. So what we didn't talk about? Oh, there's stuff missing off the slide. We have so let me add another slide to this. I'm going to do it at the end. So three-phase motors, we can wire them what we call wide. It's called that because most people draw it like this. Or we can wire it in what we call a delta. Now, what's nice about a Y is that we come over here, and if we have 208, first of all, what's nice about a Y is we have the center point. Now, what's nice about a Y is we can take the center point and we can establish a common or we can establish a ground. This is true with transformers. So transformers, I mean, if I came over here and I had 120 volts across each one of these, then what we would get across the phases, we'd get 208. Because the actual voltage is the phase voltage times the square root of 3. So this is what runs the college. That's why we have 208 here. If you're ever in motor control, we have 208. We have a ground, right? We have a neutral or a ground. And this allows us to get two different voltages off the same transformer. Over here, if I put, if this right here is 208, if this right here is 208, this right here is 208, oops, sorry, 208, and this is what we get. In fact, we don't get that. It's not times the square root of 3. The standard, what we do is 240, 240. So these usually runs on even numbers. Now, what this thing works, if this was the secondary of a transformer, then what I would do, if I was getting 1 amp out here and 1 amp out here, then each phase would only be providing 1 amp divided by the square root of 3. So this is, but we don't have a common spot to make a ground, right? You understand that? This is what power companies love to generate. They love three-phase delta because they can get what? Let's bring it on the primary delta. So what they can do is their transformers can actually be rated lower than the current they're actually getting out of it. But we have no ground. So this is why on your power poles you'll see three lines, right? And you won't have a ground. When they come into the plant though, we want to have a common or we want to have a ground, and also we want 2 voltages. So the advantage of a Y transformer is we get 2 voltages, we get a high and low voltage out of it. The advantage of a delta is that the transformers don't only have to only have to provide 1.7 less than the actual line current. Motors makes absolutely no difference right now. So these guys are designed to run at a certain horsepower. The horsepower is set by it's roughly 746 watts per horsepower. So what we're talking about, if I've got 208, how the current is divided, how it's divided back up. You know, if I've got a 1 horsepower motor, it's going to pull that current, no matter whether it's round delta or if it's round Y. Okay. So it's up to the manufacturer of the motor what they wire. In fact, they don't even tell you that, whether the motor itself is wired delta or whether it's wired Y. Where it comes into play is on a 6-lead motor. So if I put 208 over here across this guy right here, it's only going to see 120 volts. So what we do on the motor is that we have what we call a Y delta motor. And this guy has basically 3 windings on it. And then these are going to come out the terminal. So it'd be what we call a 6-lead motor. And what we can do with this is we can start it Y and then switch it delta. Now, why do we want to start it Y and switch it delta? Well, what we're doing is we're lowering the voltage inside the motor to start it. The problem we have with these big motors, we talked about this the other day. So let's say I have a 200 horsepower motor, and I start that thing up. How many horsepower is it going to try to develop when we start it? How many horsepower is this thing going to try to develop when we start it? The start current, if we don't know what we talked about this the other day, is 6 to 8 times. The voltage don't change. So that means a 200 horsepower motor could try to generate 1200 horsepower when you start it. 1200 horsepower can tear some stuff up. So what we used to do is we used to have these big old banks of resistors out there that we would come over here and we would just put a start. And what we would do when we started the motor, we would make it go through the resistors. That high current would be dropped across those resistors, and the motor could not create all that torque because it didn't get the voltage that it needed. But as soon as it got started, we would close these contacts, and now the motor would produce the horsepower that it's designed to produce. So what happens is we would have a relay. Instead of using resistors, when they're dropping all that voltage, they get real hot, and that's just wasted energy. What we'd like to do is have a way that we could just reduce the voltage at the motor without using resistors. So what they do is they have a circuit out there, and they start it Y, and when the motor gets running, they'll switch it delta, and then they get the full voltage. So these are what we call reduced voltage starters. We don't have to deal with this with these variable speed AC drives because they set a torque. So they automatically reduce the voltage and speed and everything to take care of starting these things up and letting them tear these things up. These big old motors, they literally can just starting them. They could do what? They could shear gears. They could do all kind of stuff because they create all that horsepower just trying to get the thing started. So out of US Steel, we had these, and they would automatically switch it. It'd have a timer on there. We'd start the motor. It would make it go through the resistors. After, 15 seconds, it would drop out, and then it would come up here, and the motor wouldn't tear everything up. So that'd be like you getting in your car. You got a 500 horsepower car. You get in your car and slam the gas all the way down. What's going to happen? Could tear up the transmission. By the way, I had that happen to me too. I had a gear shift, and I popped the clutch and it sheared out first gear on my transmission. Revved up the engine, popped the clutch, and I was stuck. So I was showing them how I could burn rubber in my car. But I released all that horsepower on my transmission at one time. So anybody that's ever drove in a gear shift knows that you don't pop the clutch, right? Unless you got a good transmission. So yeah.
What kind of car was it?
It was, you probably don't remember, it was a little Vega GT.
Vega?
Yeah, that thing would get rubber in 3 gears.
Oh my goodness.
Yeah, pour it up, man. And I was showing off. We were out on the road, so that wasn't close to anything. It was embarrassing. So I took it apart, was going to rebuild it, and decided I couldn't do it.
You didn't do it?
No, we found a something for about $80 probably. So that's so as far as a single motor goes, whether it's Delta or whether it's Y, it makes no difference. Only thing is these 6 lead motors, these Delta Y motors, and then you have to make sure you wire them up right, because we want to start it Y and then shift it into Delta when we get up to speed. Yeah, these big old horsepower motors. I mean, drag racing, when do they usually blow up? At the line, right? You see them shear out their transmissions. They're releasing all that horsepower on their big old motors. And that's really neat because you can see the rear wheels, the centrifugal force on the rear wheels actually make them, and the whole thing comes up. Okay, guys, so that's about it. So how do we reverse the 3-phase motor? Yeah, it's called the 2-phase. But normally, industry standard is swap L1, L2. But technically, you can do it. Well, when you do things, you want to do them according to what we call industry standards, so that way the next person that comes in there after you knows what to expect, right? And if you don't do it according to industry standards, then they talk about you. So, and of course, some companies you could lose a job. So that's motors, guys. Have any questions? Yes, no? Any questions in here?
No.
And like we said, the only motors that we have are this, but they have a gearbox on them. See, I've got. I passed that around last class. So. Oh, let's see if my camera will work on my computer. I don't know why it's shifting.
Hey, Rich, we can't hear you.
Okay. Can you hear me now?
Yes.
Okay, good. Bring the camera back up. So, like I was saying, I don't know why this is shifting. The motor's doing this noise right here. Well, what I can do with this is I can change what we call the pulse width. Now, what I'm gonna do, this is the actual motor. So right now it's stopped. I can't run it full speed. So if I come over and make the pulses bigger, this is just a regular little DC motor. I know at home it looks kind of weird because of the sync rate of the pictures. But what I can do is by changing the pulse width, I can precisely control the speed of this DC motor. You know, see that? Of course, I can see it on the camera.
Yes.
So this is called PWM, or pulse width modulation. And this is the most popular way of controlling the speed of a DC motor now. In fact, most of your PLCs will do pulse width modulation for you. So you can actually directly control the speed of a DC motor. Now normally you can hook this up to a drive circuit. My little function generator can't put that out. So what I have here is I have a transistor right here. It's a NPN. So the function generator is actually controlling, turning this thing off and on, and the actual power is coming from this power supply over here. So, but this is pulse width modulation that we talked about the other class, and they can combine pulse width modulation and actually create these variable AC drives by using negative and positive voltage. This is a stepper motor. This is only 24 steps. Okay, so this is a 24 step motor, so that'd be 360 divided by 24, which would be, what, I don't know how many steps per revolution. Well, we could calculate it. So this doesn't have near the this doesn't have near the resolution as the other stepper motor that I have has. So the resolution of this little motor, I'm from a calculator there. Yeah, 15 degrees per step. So this guy only gives us 15 degrees per step. So this wouldn't have near. We got them that's got 1800 steps. We can double step them, which means what we do is we energize two poles at the same time. We call them half step, excuse me. I think I showed y'all back here on this video. Now what this guy's doing over there, we don't know because it's going through a controller. And I don't know how many steps that motor has on it. We might could look it up. But so this is an example of half stepping on this slide right here. So what they do is they energize two poles at the same time, and then of course the permanent magnet goes in the center. So technically, this guy right here would have four steps, but if we half step it, it gets 8 steps. So you can technically take a 100-step motor, and if you half a step it, you can get 200 steps out of it, and that would be about 1.5 degrees per step now. So, but these are stepping motors, and what I'm gonna do is let me so y'all can clean it off a bit. Clean. I'll put one of our lights. Just turn it. You can literally feel it. We call it DC torque. So what we have is that we start off with these guys right here are just metal. The poles out here, These are just metal and they got wire wrapped around them. So what happens, and this right here is the rotor is a permanent magnet. So what happens, you can actually feel it. It's going to try to lock into those poles. So you can actually feel it when it tries to lock in. And of course, this would be a controller for a stepping motor. And we have unipolar, we have bipolar, we have different types. The only stepping motor that we have is the one that's running the carousel on the amateur line. All the motors on the Festo line are, and like I said, it's really neat. So it's only got 3 motions, and it's got the controller built into the thing. And it's been programmed to either move 90 degrees or move 45 degrees from its current position. So it takes very few wires to run it, and you just say move 90 from your position or 45. So if we look at that, at the carousel, but it's got to start, for it to mean anything, it's got stepper motors. If we run them open loop, of course robots, if they use stepping motors, those guys are so precise, they actually have encoders on them. So you have 2 backups. Most of our stepping motors we run open loop but we start them from a known position, right? And then if we start them for a known position, and then I step it 100 times, that might be 45, and it will go 45 degrees. If I stepped it 200 steps, then it would go 90 degrees, right? So if you ever notice the carousel, it either moves 45 or it moves 90, depending on what it's actually running. So we'll make sure we show y'all that, and you can turn it off no matter where it's at. And when we turn it on, the first thing it's going to do is home itself. It's going to find itself before it even lets you do anything with it. And so I'll show it to this group here. So what we're gonna deal with today is for this group, we're going to put some bugs into the line, into their module. Going to put a fault in there. And then it's going to be up to y'all to try to find it. So we got maintenance forms that we'll keep up with, and I'll go over those with the class, and then when this class comes in, they can do that. We've got one more primary lecture that we're going to do. It's on power. We should have already had it. And then we do have one also on soldering. We used to do soldering in this class, but we can't now because of all the stuff that's going on. But I'll introduce y'all to soldering. So understanding how to solder in electronics is pretty important. We got a lot of people that think they know how, but they don't. So what we have now is we have the entire manuals. I'm going to give the manuals out to y'all. In fact, just run off everything that comes with that Festo provided with the line. So we're going to skip over, like I said, splitting up like this is cost us quite a bit of live time, but we're getting the gist of the program. So this is going to be Amatro line module 1. So we'll make sure we look at module 1 first, and then we'll get a basic look at all the modules. So this is the oh my goodness. Might not look at module 1. I don't see combined. Y'all see one that says combined? No. Okay. So let's look at module 2. I need to do that. So here we go. So what we should find in this chart is we should find of course, the function diagrams that we just did, right? Or we tried to do. just to get y'all a feel. We knew that odds are, you wouldn't get it exactly right, the first time. So this is module 2. So it starts off with the picture that you, yes, let's see. Oh, let's see. Module 2. I didn't find the combined on module 1. And then, of course, we have one. This gives us electrical diagrams, right? Of course, we've already looked at this. This gives us how to calibrate. It's got the whole calibration procedure for the ultrasonic sensor, by the way. And then we'll try to do that. We'll try to figure out how we can split that up so everybody gets a chance to do that. Should give us the flow chart or the function diagram. Some of y'all had this, but what we didn't really look at is when it tries to split up. So this shows us what we require. So here we require let me make it bigger. So here it says we require a 4S1 and then the start button to be pressed. And it falls down into this, which affects 4S2, 4S2, and then here. Then what it does is it comes down here, it has 2 directions it can go, depending on input 2.4 and right now I don't know, I thought I had corrected this. We need to figure out what it's hooked up to input 2.4 and input 2.3. So let's and this is out of order. So input input 2.1, is that what it says? 2.1 and 2.4. So 2.4 would be one of our photoelectric sensors. And what was that? 2.1 is from the previous line, I think. Did I go past it? Should have looked at the page. Okay, here we go. Says it needs 2.4 and 2.3. And if 2.4 is true or false, so that's what the line means above that, and 2.3 is true, then it'll take this path right here. If 2.4 is true and 2.3 is false, then it'll take this path right here. So this must be, this is module 2, so this must be white reject. So we, in ours, none of y'all figured this out, but I figured that, right? Well, there's a flow chart. Here's the step chart. Or 2 parts of the step chart. And you can use either one of those. This is a nice chart in that this actually shows you the condition of the PLC, the inputs of the PLC for each cell. If it don't show it, it means it stayed the same. So what they're saying is here, if I go down there right now and before I press the start button, if it's in the reset position, then these inputs should be like this. So if it's got a 1, that input should be on. If it's got a 0, it means the input should be off. And this should be the state of the output. So all the outputs should start off. And then step 1, this is going to be a 1 or a 0, depending on whether the start button is pressed or whether it's not pressed. This is still going to be a 1, this is still going to be a 0. So if they don't show it changing, it's going to do what? It's going to stay the same as the previous step. So this would actually be the step chart, depending on what condition is true as far as the part goes. So this is a really good troubleshooting aid that they came up with. So if it don't start at all, then what you could do is just look at your PLC and find these positions. I showed you how to identify those, right? The inputs and outputs, how to get 0, 1, and stuff like that. Then we pull the little doors off and show it to you how to read those. Yes, no? We'll go back and review that. Okay. So that's interesting. That's a really good chart to find right off the bat. This we've never used. And that's about, so the 2 main things, or the 3 main things that you would use to try to figure out where it's stalling at is either your step chart or your function chart. And different people refer different things. But remember, on the step chart, this is when things are in motion. This is what's required to cause it to go into motion. Y'all understand that? I think I all did pretty good on the test. So what we'll go back there. By the way, this shows you the names of all the different things and what they are. This is the diagram, and how this got out of sequence, I don't know. This guy, I don't know if it's actually out of sequence in the actual book or not. So we looked at all the symbols, right? Y'all okay on all the symbols? Y'all on these symbols like this? Y'all know these? Are we okay? All right. Look at a bunch of symbols. And those are output, and those start on out. This shows you the wiring of the terminal block. That the PLC connects to. So the PLC actually connects to these ports. So that might be a little easier. I don't think it's actually labeled. I don't know. It's not actually labeled, I don't think, on the terminal board itself. So what we're going to do is questions. Okay. So this is the actual maintenance form. So you'll have 2 forms for these. You'll have one for the lab, for the credit for the lab, and then a maintenance form like you would fill out at some places. Most of them do that just to keep up with stuff, with complaints of customers and stuff like that, so they can tell what we've done. So labs, and this is the maintenance form. This is the example. We did the step chart. We did the function charts last time, and y'all presented them, right? Yeah, I gotta have it left on. I gotta run off. So once we get started, guys, I'll go up there and run off. Thanks for reminding me. So all this top is already filled in. So what you'll do is, normally we try to work in teams of 3. Of course, we can't do that. And then what we do during the class is we rotate y'all between teams. So everybody has a chance of being the leader. The leader is the person that basically, they present their troubleshoot procedure. So you need to get your whiteboard, you need to clean it off and keep up with what you did to find your part. And then you'll have to present that to the rest of the class. I'll put what time it was received. I'll put the module number in there. And then what you'll do is you'll put the time that you put it into work. So when you get back there, what time did you put it into work? And then what time, did you complete it? And then I put the problem in here. That's me. And then you need to put what you did, right? And then if you simulate replacing any parts, which we'll try to do that too, where you'll actually remove the part and then take the same part and put it back on, what you did. That'll be one of our labs. This, you got the handout. This will be, the lab number is lab 6, which would be called troubleshooting 1. So that'll be the title of it. And so this is basically what your lab form will do. You're also going to have not a lab form. This is your maintenance form. You also have a lab form. So normally when we work with a team, you have one lab form per team. You have one maintenance form per team, and then you have one lab form per student. So we got problems back there, and of course it's up to you now to try to figure out what Rich did. So group 2, I guess this is it for you today. If you hadn't got any questions, y'all got any questions? I'm listening. Now, next Tuesday and next Thursday, the whole class is coming in, because we'll be doing a test on Tuesday and we'll be doing a test on Thursday. Group 2, you can either come in and sit in the entire class, or I know how we do it. We'll do lab. So group 2, y'all just come in and time to take the test. Okay. So we'll be in lab the whole time on Tuesday, not Thursday. On Tuesday. So we'll be in lab the whole class besides for taking the test. We will give the test at the start of class next Tuesday, and that way we can go over the test before y'all go home, right? Understand if there's anything wrong with it. So what'll happen is, and then after the final exam, we'll take the final exam at the start of class, and we won't be doing any lab after that. So whatever we get to Tuesday, that'll be it. Okay?